start.
Okay, well, so thank you very much. Thank you for the kind invitation. It's my great pleasure to be able to give this talk. I almost messed up my time zones, but yesterday evening before going to bed, I thought I'd check again because we have already moved away from daylight savings time last week, whereas I think you haven't. So I just almost messed up my time zones, but fortunately that didn't happen. So yeah, the topic I want to talk about today is neutrino magnetic moments, both in the standard model and then especially in extensions of the standard model. And I'm going to give you a kind of broad overview of the topic, including both terrestrial and astrophysical cosmological constraints. So here's the plan for the talk. I'm going to start by introducing what a neutrino magnetic moment is and why we're maybe interested in it. Then I'm going to spend some time talking about measurements of neutrino magnetic or searches for neutrino magnetic moments in dark matter experiments. And in that context, I will also comment on the recent XENON1T anomaly. I will then present you a potpourri of constraints, in particular from Big Bang nucleosynthesis, turns out to be one of the most important ones. And finally, in the end of the talk, I will present some model building considerations and outline some possible connections between the physics of neutrino magnetic moments and the physics of beam meson decays, where some anomalies have been seen as well. Okay, but let's start with neutrino magnetic moments in the standard model and beyond. So a neutrino magnetic moment is a prediction of the standard model. If you look at the two Feynman diagrams at the top of this slide here, you see how it's generated.
Hello?
Yeah.
I don't see your screen. How about other people?
Oh, I can see the screen.
Okay. Then my terminal has a problem. Okay, thank you. Please go ahead. I will try.
I'm sorry about this. Is it maybe there's in the top of the Zoom window, there's this small button where you can switch between seeing the participants and seeing the screen, perhaps? I'm sorry about that. Yeah, so if you look at those two Feynman diagrams here, this is how a neutrino magnetic moment is generated in the standard model. Essentially, a neutrino goes to a loop consisting of a charged lepton line and a W boson line, and then back to a neutrino. And since the particles traveling here in the loop are charged, it is possible to attach a photon line. And yeah, that is then what leads to the neutrino magnetic moment. The magnetic moment is a property that also a neutrino at rest possesses. So it's a zero momentum transfer object. So it can be always thought of as an effective dimension 5 operator. Down here, I show you what this operator looks like both for Dirac neutrinos and for Majorana neutrinos. So for except that I think I just mixed up the two equations. So the left one is for Majorana, the right one is for Dirac. I'm sorry about that. So for the Dirac case, there is the fermionic tensor current, nu L bar, nu right, multiplied by the electromagnetic field strength tensor. And the coefficient up front here, which has mass dimension -1, that's the actual magnetic moment. So the thing to remember here is first, it's dimension 5. So the magnetic moment is a dimension-full quantity. And second, it's a tensor current. That means it couples left-handed and right-handed states. And this is also the reason why neutrino magnetic moments are fairly small in the standard model. So the rough scaling of this diagram is shown here. So the magnetic moment, of course, must be proportional to the electromagnetic coupling constant because there's a QED vertex here. It should be proportional to the Fermi constant because there's two weak vertices here and a W propagator. Then there's a loop factor 16 pi square. And very importantly, there is a factor of neutrino mass. And the reason this neutrino mass has to be there is because a magnetic moment couples left and right-handed states, whereas the weak interaction couples only to left-handed states. So the incoming neutrino must be left-handed. The fermionic line must stay left-handed throughout the loop, otherwise the second vertex here would be forbidden. And then the spin flip must happen on the outgoing neutrino line. So a spin flip on a fermion line comes with a fermion mass insertion. And since the neutrinos are extremely light fermions, that's unfortunately a very small mass. And for this reason, the neutrino magnetic moment is only about 10 to the minus 20 times the Bohr magneton. So the Bohr magneton is like the generic magnetic moment you expect for, that's the order of magnitude of the magnetic moment of an electron, for instance. So the neutrino has a magnetic moment that's 20 orders of magnitude smaller than this in the standard model, precisely because the neutrinos are so light. Now, we are nevertheless searching for neutrino magnetic moments, and here are two types of experiments that currently give the best terrestrial limits. So there are also astrophysical limits about which I'm going to talk on the next slide. But for terrestrial limits, these here are the strongest ones. So the first one is Borexino. As you may know, Borexino is a solar neutrino detector where the main detection channel is the scattering of neutrinos on electrons. Now it turns out that this scattering process can be enhanced if the neutrinos have a magnetic moment. And by doing this, so Borexino looks at their precise electron recoil spectrum. They have an extremely sophisticated background model, and then they look for deviations of the observed event rate from that background model. And by doing this, they get a limit that's 2.8 times 10 to the minus 11 Bohr magnetons. So that is still about 9 orders of magnitude above the standard model prediction, but also it's 11 orders of magnitude below, for instance, the magnetic moment of an electron. So this is an extremely precise measurement, but it still doesn't quite get us to the standard model value of the neutrino magnetic moment. A similar approach can be pursued at nuclear reactors. There's in particular an experiment called Gamma in Russia that has done this. So they use electron antineutrinos from a reactor and allow them to scatter on electrons. Once again, they look at the electron recoil spectrum and look for an enhancement there. They don't see any enhancement, so they set a limit that is about as strong as the limit we get from Borexino. Now, an even more sensitive way to search for neutrino magnetic moments is in astrophysics. And here, the most important probes are stars and supernovae. In stars, the idea is that through this magnetic moment coupling, if you remember, the neutrino magnetic moment coupled a photon to 2 neutrino lines. So this in particular can lead to the efficient production of neutrinos inside stars. So in a sense, what you can imagine is that inside the hot plasma of a star, the photon is not strictly massless, but it receives an effective in-medium mass. So the photon effectively becomes heavier than the neutrinos. So photons can decay to neutrinos. Now, photons are trapped inside a star because a star is opaque. Neutrinos, on the other hand, can freely escape. So if this process is allowed, that an in-medium photon, a so-called plasmon, that a plasmon decays to neutrinos, if that's possible, then this means the star will lose a tremendous amount of energy because there's plenty of photons in the star that normally could not escape but would be reabsorbed. But now they can decay and the decay products can escape. So there's a huge energy sink. And this would mean that the stars, in order to maintain the observed temperature, would need to burn through their fuel much more quickly. So by observing the properties of stars, for instance, by observing how old they are and by observing their evolution, one can set very, very strong limits. The current best limit from this method is a magnetic moment of about 2 times 10 to the minus 12 Bohr magnetons. So that's an order of magnitude stronger than the best terrestrial limits, but it's still about 8 orders of magnitude away from the standard model prediction. Similar arguments can be made for supernovae. In a supernova, the most important process is the conversion of left-handed neutrinos to right-handed neutrinos by coupling to the photon field. So in a supernova, even left-handed neutrinos are trapped inside the core, but right-handed neutrinos are not. And therefore, this process of left-handed to right-handed neutrino conversion can also lead to extra energy loss. This would mean that the supernova core cools faster, and we would not be able to explain the observed duration of the neutrino burst from supernova 1987A. Once again, the limit is of order 10 to the minus 12 Bohr magnetons. So comparable to the stellar cooling limit, but an order of magnitude better than the terrestrial limit. I will comment more on supernova limits later, in particular on possible ways of avoiding them. Now, since we've seen that our current experimental techniques don't quite get us to the standard model of the neutrino magnetic moment, let's look at the possibility that the neutrino magnetic moment is larger in the standard model. This happens quite generically in theories beyond the standard model. And by far the simplest option is that there is a singlet fermion, let's call it a sterile neutrino or a heavy neutral lepton. It has many names, but it's always the same thing, a singlet fermion. I will comment on other model building possibilities later. So if a new singlet fermion exists, then it can take the place of the right-handed neutrino in this magnetic moment operator that you see here. So it's now a coupling not between active neutrinos of different flavors, but it's a coupling between the left-handed active neutrino and this right-handed or sterile neutrino. So this means that in particular, through this operator, left-handed neutrinos can be converted to sterile neutrinos via a coupling to the electromagnetic field. And this brings us to the next part of my talk. Yeah?
May I ask a question? Oh, yes. Right. It's just out of my curiosity, but about the lab experiment, Borexino and the gamma.
Yeah.
I'm wondering if it depends on whether Majorana are the neutrinos of Majorana or drag, because it's involved in Majorana case, it should involve the flavor violation, right? To write down the magnetic moment.
I think the experimental technique works for both cases, Dirac and Majorana, but the theoretical interpretation is different. So as you say, for instance, for Majorana neutrinos, a flavor diagonal magnetic moment would be forbidden, whereas flavor off diagonal magnetic moments, so-called transition magnetic moments, are allowed. So the theoretical interpretation is different. So imagine if one of those experiments measured a particular value of the neutrino magnetic moment, then translating this back into, say, the properties of a given BSM model, that would depend on whether it's Dirac or Majorana. So there's at least a factor of 2 difference typically, and then of course the fact in one case it has to be diagonal, in the other case it has to be off diagonal.
Yeah, because you've shown just only single numbers for each, so I just wonder if it should be depending on whether it's Majorana or drag. So even though the change is just quite little.
So if we were able to measure the standard model value of the neutrino magnetic moment, then this would be a way of distinguishing Dirac from Majorana neutrinos. But yeah, unfortunately, we are still many orders of magnitude away from that.
Right. Okay. Thank you.
Okay. Thank you. So, right. I wanted to talk about how we can measure neutrino magnetic moments in direct dark matter searches. This is a fairly new technique, but it's poised to be very soon the most sensitive, at least terrestrial probe of magnetic moments. So let's look again at the neutrino magnetic moment operator. For generality, I'm writing down here already, oops, sorry. Yeah, I'm writing down here already the version beyond the standard model with a singlet fermion, because only in that case we can hope to get a positive signal. And once again, the signal one would be looking at is the scattering of neutrinos on electrons or nuclei. In particular, we would use solar neutrinos simply because this is the most abundant neutrino flux we have at hand. This process of solar neutrino scattering on electrons, it's of course well known in the dark matter community because this is this causes the so-called neutrino floor. So this causes the irreducible background that dark matter searches will hit upon very soon. If you look at these somewhat busy plots, it shows you what this background looks like. So in both plots, the horizontal axis is the recoil energy. In the left plot, it's the electron recoil energy. In the right-hand plot is for nuclear recoils. So this is the energy that a direct detection experiment would measure. On the vertical axis, we show the expected number of events per keV. If you look at the black curves, these are the standard model predictions. The dotted one here is for just the muon neutrino flux. The dashed one is for the all flavor flux. You see that at very low energies, well below a keV, or maybe below 10 keV, this is pretty flat. And then at higher energies, it has these steps. And these steps are simply a reflection of the complicated structure of the solar neutrino spectrum. So the solar neutrino spectrum receives contributions from a number of different nuclear processes. And each of them has a characteristic neutrino spectrum with characteristic cutoff energies. And whenever one of these processes starts to contribute to the spectrum, we see this kind of step. The plot also shows data for comparison. You see data points labeled Borexino. These are the data points that have already been used to set limits on magnetic moments. And on top, you also see the data points from the XENON experiment. Now, if you now look at the colored curves, so the colored curves are now for scenarios with a sizable neutrino magnetic moment. The blue one is for a transition magnetic moment to a fairly light sterile neutrino. That's basically equivalent to phenomenologically, that's equivalent to a magnetic moment that just couples active neutrinos to active neutrinos. And then the red curve is for a transition magnetic moment to a heavier sterile neutrino. So the most striking feature is the steep increase of the number of events towards lower energies. And this is precisely why direct dark matter searches are such a good option for measuring neutrino magnetic moments, because they have much lower thresholds than, say, dedicated neutrino experiments like Borexino. So even though in terms of absolute flux, their sensitivity is maybe a little worse because they are smaller, they make up for this because they can go to such low energies. So they really see this rising part of the spectrum. Yeah, and of course, if the neutrino you're transitioning to is heavy, as shown here for the red curve, then the whole thing gets again shifted to the right because some energy needs to be invested in order to make those sterile neutrinos. So let's also look at the nuclear recoil plot on the right. There the picture is similar, except now most of the neutrino spectrum lies at even lower recoil energies where they are very hard to see for experiments. So you see that the XENON data points here, they just see the very highest energies of the spectrum. So for this purpose, really electron recoils is the way to go. I already mentioned this strong enhancement at low energies. It's easy to understand why this enhancement is there, namely the scattering process of a magnetic dipole, or a neutrino with a magnetic moment on an electron, proceeds through a photon. So the process has the propagator of a massless particle in it. So there is the energy appearing in the denominator of the amplitude. And this is why lower energy gives us an enhancement here. For the standard model scattering process, so the black lines in these plots, that is mediated by the W boson. So their energy does not appear in the denominator, but only in the numerator. So there is no enhancement at low energies. But for the magnetic moment, there is. Okay, now let's look at the XENON data a little more carefully. As you know, XENON reported earlier in the year, I think in June, a rather exciting observation, namely a small excess of electron recoil events. So this is what their full spectrum looks like. This here goes from energy 0 to energy 200 keV. And if you superficially look at this plot, you would say, oh, well, but this matches perfectly well their background model. The axis they are talking about is actually here in these very low energy bins. So it's very hard to see in this plot, but it's much easier to see if we zoom into that region. So here's what we have here. The red curve is the best fit background model. The black points are the data points. And what you notice is that in particular, the lowest data points are somewhat high, and the statistical significance of this amounts to roughly 3 sigma or so. So it's not tremendous evidence yet, but it is certainly something to watch out for and see how it evolves in the future. Now, when you look at this, the spectrum rising towards lower energies, this is precisely what a neutrino magnetic moment would predict. So among the explanations of the XENON1T anomaly that exist in the literature, the neutrino magnetic moments are certainly one of the ones that are worth considering. So we've done this, we have taken this spectrum, we've fitted a neutrino magnetic moment, and we get the following. So this is a rather busy plot through which I will walk you step by step in this talk. For now, let's focus on those items that I've circled in green here. So first, you see this purple region down here, the one labeled XENON1T axis. This is where a neutrino magnetic moment would need to be in order to explain the xenon axis. So these are our 1 and 2 sigma contours. So you notice that this is at the required magnetic moment here is few times 10 to the minus 11 Bohr magnetons. We have here assumed couplings to only one neutrino flavor, but of course it works also if couplings are there to other neutrino flavors. Now, a coupling of this magnitude is consistent with terrestrial constraints, but it will be inconsistent with astrophysical and cosmological constraints. And I will discuss those a little further later in the talk. But for the moment, this purple region is what we get if we just take the xenon axis at face value and try to fit it with a neutrino magnetic moment. The vertical width of this region, that just comes from the measurement uncertainty, and the fact that it only goes up to a right-handed neutrino mass here of about 0.1 MeV, this is just a kinematic cutoff. So at some point, the solar neutrinos no longer have enough energy to make these sterile neutrinos and still give a sufficient electron recoil in xenon. So this is why this region here ends somewhere. And if you take instead the hypothesis that this is not a magnetic moment with a sterile neutrino, but a magnetic moment among the standard model neutrinos, then you'd essentially be sitting at the very left edge of this purple region. But in this case, you run into many more constraints. So I think magnetic moment among the standard model neutrinos will not work for xenon. A magnetic moment with a sterile neutrino might just marginally work, perhaps. But I'm going to go into this in much more detail later. Of course, besides explaining the axis, we've also tried to do the conservative thing and just set the limit. In order to set the limit, we have entertained the possibility that the axis that xenon is seeing is not because of a neutrino magnetic moment, but because of an unaccounted for background. So xenon themselves in their paper entertain the possibility that there is tritium in their detector, which in the case of those tritium atoms would contribute to the electron recoil spectrum in a similar way. They quite conclusively argue that this cannot be the case because the amount of tritium they would need in order to explain the axis would be so tremendous that they would have seen it in many other places. So if there was tritium leaking into this detector, then many other things would need to be leaking in as well, and the detector would basically be blind. So this tritium explanation is in my opinion, not a plausible explanation, but it is within the standard model. I think it's the best explanation we have at the moment, the true explanation we just haven't hit upon yet. So doing this, so including a potential contribution from tritium in the fit, the axis of course goes away. So we no longer get closed contours, but we get an exclusion limit. And this exclusion limit is shown here as this dashed black line. For comparison, I show also the limit that XENON1T would set if they were only looking at nuclear recoils rather than electron recoils. And this is the solid black curve here in the top part of the plot. As you can see, the sensitivity is many orders of magnitude worse than for electron recoils, except in the case that we make the sterile neutrinos extremely heavy, then the sensitivity of electron recoils peters out faster than the sensitivity of nuclear recoils. But that region up here is anyway excluded by many other experiments. So that's not really an interesting region. Okay, now this was about XENON1T. Are there questions up to this point? Because I would next proceed to discuss all the various limits that are shown in this plot. Okay, if not.
Hello, I have just a minor question, but about the Borexino constraint, about mass range nearby MEV, there's some bump and fluctuation. I just wonder what causes this. Yeah.
You mean this wiggle here?
Yeah.
So this can be understood if we look back at the Borexino spectrum. Here it is. So you see that the Borexino spectrum is rather irregular. This is because there are contributions from many different radioactive decays that can happen in or near the detector. And when one of the peaks of your predicted signal lies underneath one of these peaks, then the sensitivity drops. And then as you change the mass, the peak of the signal moves in and out of these peaks. And this is why the limit in the end has these irregularities. So that has to do with the way the backgrounds work in Borexino.
I see. And also this, this bump can only be seen in an electron recoil, but not be seen in a nuclear recoil, like in xenon. The constraint figure.
So the I mean, Borexino only looks at electron recoils. In xenon,
there are two, right? The nuclear recoil and electron recoil, and only electron recoil line shows this bump, but in a nuclear recoil, it's just smooth.
No, wait. Let's go back to the constraints plot. Just a moment.
Yeah.
So Borexino here, Borexino is only electron recoils.
Yeah.
So if you look at xenon, it is true that the electron recoil spectrum here is less regular also for xenon. But this is because the electron recoil surge in xenon, this is also a surge that is affected by numerous backgrounds. So they are in a similar situation as Borexino. So there are bumps and dips in the background spectrum, and these make the experiment more or less sensitive depending on the right-handed neutrino mass. The nuclear recoil surge, on the other hand, is essentially a background-free surge. And therefore you don't have this competition between signal and background. You have your signal and that's it.
I
therefore this is much smoother.
I see. So can we understand that in the way that this bump and dip will be some systematic errors?
I wouldn't say they are systematic errors. They are systematic effects. So they are. I mean, the background is there, but the background is quite well understood. It just means that there are particular regions of the spectrum where the experiment is less sensitive than in other regions of the spectrum.
I see. I see. Okay. Thank you.
Okay. Thanks for the question. Okay, now let me talk about all the other constraints that I showed on the previous plot. I'll show that plot many more times and then explain all the various constraints to you. One constraint that I would like to go into a little bit of detail with is Big Bang nucleosynthesis. That is not an entirely trivial constraint. That is why I will take a few minutes to explain it to you. So let's consider once again this situation that we have the standard model plus a sterile neutrino, and there's a magnetic moment operator that couples the two. If these right-handed neutrinos, we assume they are somewhat heavier than the active neutrinos, so their cosmological history will depend very much on when they decay. If they decay long before BBN, then no harm is done. Any effect of their decay will be washed out. The energy will be reabsorbed into the thermal plasma, and we will not be able to see it. But if they decay during or after BBN, then there can be tremendous effects. I here would like to walk you in particular through the case that these right-handed neutrinos decay after BBN. So imagine we have a right-handed neutrino. We make it at early times in the universe. They are abundant. But they have a relatively long lifetime, so they live through BBN. This typically means that they are lighter than about an MEV. So the first consequence of this is, well, if they decay after BBN, they are still around during BBN. So their energy density contributes to the total energy density of the universe during BBN. And this means that the universe expands faster while BBN is going on. This means, on the one hand, that the time during which protons and neutrons are still strongly coupled to each other is shorter. So remember that at early times, protons and neutrons can be converted into one another quite efficiently through the weak interaction. And then at a temperature of about 1.2 MeV or so, these conversions freeze out. Now, the time at which these conversions freeze out determines the relative abundance of protons and neutrons, because there's a small mass difference between protons and neutrons. So the thermal abundance of neutrons depends on when exactly they freeze out. Now, if they freeze out sooner, there will be more neutrons. On the other hand, there will also be less time for neutrons to decay afterwards. So after protons and neutrons have decoupled, they both evolve separately until they eventually get bound into nuclei. And during the time in between the decoupling of their interconversions and the time that nuclei actually form, the neutrons just decay. And if there is less time, because the universe is expanding faster, then fewer neutrons will decay. There will be more neutrons in the end, and all those neutrons get bound into heavy nuclei. So there will be more heavy nuclei, in particular more helium. So that's the effect of the right-handed neutrinos being present during BBN. But of course, they will eventually decay. And this also has important consequences, because when they decay, their decay mode is into a left-handed neutrino and a photon. So upon their decay, they inject energy into both the neutrino bath and the photon bath. The fact that they inject energy into the photons means in particular that the baryon to photon ratio changes. We have assumed that this happens after BBN. So what will be modified is the baryon to photon ratio at the CMB epoch. However, at the CMB epoch, we have a very, very precise measurement of the baryon to photon ratio, because the baryon to photon ratio controls how efficient the plasma oscillations are that make the wiggles in the CMB. So we can say that this baryon to photon ratio is essentially fixed at the CMB epoch. This means that if the baryon to photon ratio has decreased between BBN and CMB, it must have been larger during BBN than it would be in the standard model. And if the baryon to photon ratio is larger at BBN, this means that there are fewer photons per baryon. And this in turn means that nuclei that you may have formed are less efficiently disintegrated. So one of the big bottlenecks of BBN is in particular deuterium disintegration. So deuterium, as you may know, is very loosely bound. So it gets very easily dissociated again by interacting with a photon. And if there are fewer photons around, then this process is less efficient. So this means in the end, we will have more deuterium. And since deuterium is the progenitor for all heavy nuclei in BBN, this means that in general, we will have more heavy nuclei. So these are the kind of arguments that allow us to set limits from BBN. And one can make similar arguments for the case, for instance, that the right-handed neutrinos decay during BBN or, yeah. And so putting all of this together, of course, the arguments I've made here, they are quite qualitative. In order to get quantitative estimates, we have to resort to numerics. So we've done that. We have used a code called AlterBBN, in particular a modified version of this code that our colleagues from Hamburg have developed. So what AlterBBN does is it essentially runs a nuclear reaction network. So it solves a set of Boltzmann equations that describe the formation of heavy nuclei. But in order to do that, it needs a number of inputs. And this is actually where the challenge lies. Because essentially you need to, as an input, you need to give it the evolution of the universe as a whole. So in particular, it needs, as a function of the photon temperature, the time, the neutrino temperature, the Hubble parameter, and the photon number density. So this is something you as a user have to do yourself. So you have yourself to keep track of the abundances of all the species in your universe at any given moment. In order to do this, we solve the following set of Boltzmann equations. So we have a Boltzmann equation for the photons, we have a Boltzmann equation for the electrons, we have one for the neutrinos, and we have one for the right-handed neutrinos. And the terms that you see here on the right-hand side, they show the rates of the different processes that produce or destroy each species. I'm not going to walk you through all the terms, but I'm just going to highlight a few of them. First, each equation contains a term that describes Hubble expansion. So of course, the energy density of each species gets depleted simply due to Hubble expansion. So this must be taken into account in the equation. So there is such a term in each equation. Then a very important process is the annihilation of electrons and positrons, because that happens during BBN. So it is not directly related to BBN, but it happens during BBN. So whatever it does to the evolution history of the universe, so to the expansion speed, for instance, is going to be very important to BBN. So we have to include a term for E plus E minus annihilation. That term appears in particular in the Boltzmann equation for the photon, because E plus E minus annihilation makes photons, and it appears in the Boltzmann equation for the electrons because, well, E plus E minus annihilation destroys them. Then there is, of course, a term that describes right-handed neutrino decay. That term appears in the equation for photons, it appears in the equation for neutrinos, and it appears in the equation for right-handed neutrinos. Because remember that the decay is a right-handed neutrino goes to a photon and a neutrino. And what is also common to all of these terms is that they come with factors of the form some energy density minus some equilibrium energy density. So as usual, all of these processes try to drive the system towards thermal equilibrium. And whether they succeed in driving it towards thermal equilibrium, well, that depends on their coefficients, so on their rates. Okay, finally, we also include the possibility that electrons and right-handed neutrinos scatter on each other through the magnetic moment. So here is the limits that we get. They are shown here in terms of the right-handed neutrino mass and the right-handed neutrino lifetime. I'm going to put them on the plot of right-handed neutrino mass versus neutrino magnetic moment in a moment, but on this plot, it's easier to understand the general features. So first of all, the allowed region here is in white. So if you look at the bottom right-hand corner of this plot, that's all white, because these are relatively heavy right-handed neutrinos that decay relatively quickly. So in other words, they will be gone by the time that BBN starts, so BBN is not sensitive to them. If you make your right-handed neutrinos lighter, so you move here into the left-hand part of the plot, this is the scenario I discussed before. They will decay after BBN, so they will affect the expansion rate during BBN, and they will affect the baryon to photon ratio after BBN. And therefore, much of this region is excluded. In the upper right-hand corner, the situation is similar. So these are right-handed neutrinos that are very heavy, but very long-lived. So they have a tiny magnetic moment, so they are long-lived, but they are still very heavy. So in this case, again, they decay after BBN, so they affect the expansion history during BBN, and they inject energy after BBN. And in this case, if you make them so heavy, it's even worse, because in this case, they start to dominate the energy density of the universe. So you go through a phase of intermediate matter domination, right when BBN is happening. And clearly you don't want BBN to happen during matter domination. So that possibility is definitely excluded. There's also this funnel region here. This is kind of a sweet spot where the right-handed neutrinos, they have appreciably heavy and have a reasonable lifetime. So what happens in this case is that the right-handed neutrinos, they are produced at very high temperatures, but they stop being produced just before the QCD phase transition. So any right-handed neutrinos that were produced already are diluted because of all the entropy that is produced during the QCD phase transition. So even though they are around during BBN, their relative abundance has been diluted. And therefore, this funnel region here is allowed by BBN. if we extended this plot to even higher lifetimes, then eventually this would get closed as well. But so that's the kind of the physics that you see in this plot.
Excuse me.
Yeah, please.
Could you go back to the previous slide, the equations?
Mm-hmm.
And yes, so maybe there'll be the plasmon decay as well if you have the extra anomalous moment. So that seems not included in
no plasmon decays. Plasmon decays. We did include them, and we checked that they are never the dominant process. Therefore, I have omitted them here, but we looked at them and checked their effect.
I see.
We have made this plot that you just saw. We have also made it with plasmon decays included, and it looks exactly the same. So we just left them out of the equations in order to not make the equations even longer.
Oh, yeah, I see. Okay, yeah, thank you.
But we checked that. Okay, so much for Big Bang nucleosynthesis. Of course, another constraint to worry about is the cosmic microwave background. Here, the main concern is once again the effective number of neutrino species. The way this is affected is if the right-handed neutrinos decay, they decay into both neutrinos and photons. So they change the energy density of both neutrinos and photons in the same way. But this means in particular, they change the ratio of the two. And the ratio of the neutrino to photon density is essentially what an effective measures. And therefore, we can use the ineffective constraint from the CMB to also set limits on neutrino magnetic moments. And you see that the qualitative features of this plot are not so dissimilar from the BBN plot. In particular, there is again a region here where the limit is relatively weak, once again, because this is the region where right-handed neutrinos stop being produced just before the QCD phase transition. So any right-handed neutrinos that you have already produced are quite efficiently diluted. Okay, now let's put those constraints back on our summary plot. Here on the horizontal axis, I remind you, this is again the right-handed neutrino mass. And on the vertical axis, this is now the neutrino magnetic moment. So we've essentially translated the lifetime from this plot into a magnetic moment. Here, the blue curve here, so the blue dashed curve is the CMB constraint. So this is if you take the CMB constraint at face value, which maybe we should do. So you see in this case, it's a pretty strong constraint. In most of the parameter space, it is the strongest constraint. And in particular, it excludes the possibility that the XENON1T excess is explained by neutrino magnetic moments. Now we can be a bit more aggressive and relax the ineffective constraint on the CMB a little, because we know that increasing an effective decreases the tension in the Hubble parameter. Remember that there is this tension between local and cosmological measurements of the Hubble parameter. That's one of perhaps the biggest problem of modern cosmology. And we don't know really what causes this, but whatever causes it, it is likely related also to n effective. So if I talk to my cosmology friends, they tell me, okay, if delta n effective was 0.3, then we would feel perfectly comfortable with this. And therefore, we have here put also indicatively a curve labeled delta n effective equal 0.3. So this means a deviation of 0.3 from the standard model value. And in this case, you can see that the CMB limit gets quite significantly relaxed. And then there might even be a region where the CMB limit does not disfavor the XENON1T excess region. But as I said, this really depends on whether we trust the delta n effective, the n effective limit at face value, or whether we assume that there must be some unaccounted for effects that cause the Hubble tension. Okay, we also show here the BBN limit. That's the red curve. You see here once again this funnel region here. This is what causes the limit to have this a sharp dip here. And once again, depending on how aggressive you are there might be maybe a small region where this might be just marginally compatible with the XENON1T excess, but really just marginally. still we cannot exclude it. Okay, so much about the cosmological limits. I would like to briefly also talk about the other limits that are shown in this plot, in particular the astrophysical ones. Here in purple, I show the stellar cooling limit. This is similar to the method I discussed in the very beginning of my talk, where we use the energy loss in stars as a means to constrain neutrino magnetic moments. This, of course, works only if the right-handed neutrino is light enough to be actually made in the core of a star. And therefore, this limit is only sensitive here at right-handed neutrino masses below, say, 0.1 MeV or so. The supernova limit goes to much higher energy. So this is the gray dashed line here. So if you look at this line, you might think immediately, okay, well, this puts an end to any hope of setting meaningful limits using direct detection. Now, the reason we show this in gray here is because there has recently been some work arguing that maybe supernova 9087A was not what it seemed to be. So if we use supernova 9087A to set limits on stuff, we usually do so by assuming that the neutrinos that we observed were radiated off the very core of the supernova. And then we use the cooling time of that core to set constraints. However, these people here, Barr, Bloom, and D'Amico, have argued that there is another possibility. There's the possibility that material that is accreted onto the forming core gets heated up so much that neutrinos are efficiently emitted from this infalling material. So this would mean that the neutrino signal we observe would not be coming out of the core, but would be coming out of the accretion flow that is falling into the core. And in this case, the neutrino emission would not be related to the time scale over which the core cools or over which the star cools. And therefore, in this, if this hypothesis is indeed true, then the supernova limit here would completely vanish. This is why we are showing it in gray dashed here. But of course, if supernova 9087A is a regular core collapse without much accretion going on, then this limit would hold. Okay, finally, let me briefly comment on this gray region up here. These are constraints from terrestrial beam dump experiments, where basically you take a neutrino and you try to make the right-handed parts in the laboratory and then look for their decays. Okay, now in the last couple of minutes of my talk, I would move away from this very phenomenological piece of work to slightly more theoretical developments, namely model building considerations. So I've talked a lot about neutrino magnetic moments in the standard model and beyond, but what I called beyond the standard model so far, this was just a dimension 5 operator. I've just written down a dimension 5 operator without going into details on how this might be generated. So this is what I would like to fix now. First of all, the most important thing to realize when model building with neutrino magnetic moments is that there is an intimate connection between neutrino magnetic moments and neutrino masses. In particular, any Feynman diagram that generates neutrino magnetic moment is very likely also contributing to neutrino masses when the photon line is removed. So here's an example for a particular model that I'll say a bit more in 1 or 2 slides. So what you see here is a neutrino is converting into a B quark and a leptoquark. That's just one of many BSM possibilities. There's a coupling to the Higgs and a coupling to the photon. Now, if you look at this diagram, you can imagine removing the photon. If you remove the photon, then this diagram makes a contribution to the neutrino mass. And this is what I meant when I said there is this intimate connection between magnetic moments and neutrino masses. In fact, this can be put into a rather generic relation, which is shown here, namely that the neutrino magnetic moment in units of the Bohr magneton is similar to the electron mass times the neutrino mass divided by the square of the new physics scale. So for this particular case here, this new physics scale would be, say, at a TeV or at 100 TeV, wherever we put the leptoquarks. So this would lead to, this would be lambda, and then the neutrino masses we know. And if we plug in numbers, we find that for new physics at 100 GeV, the observed neutrino masses would correspond to a neutrino magnetic moment of 10 to the minus 10 Bohr magnetons. So that is an order of magnitude stronger than the best current limits. No, sorry. If we, no, the other way around. If we want a neutrino magnetic moment of 10 to the minus 10 Bohr magnetons, then this would mean that we should have neutrino masses that are way larger than in the standard model and way larger than what we observe. And this is why generically, if you want to have neutrino magnetic moments from new physics at, let's say, the TeV-scale, then typically there is at least a small amount of tuning involved. Unless there is a symmetry that helps you. One such symmetry is called the Voloshin Mechanism. The idea behind the Voloshin Mechanism is simply that you introduce an approximate global SU2 symmetry. That symmetry can, in more complete models, that can be related to the breaking of some even higher scale symmetry. But at the electroweak scale, it would be an approximate global symmetry. It would be broken by the mass terms, but other than that, it would be exact. And in this global SU2, the left-handed and right-handed neutrinos are parts of the same doublet. Now, if you put them into the same doublet, then it turns out that a mass term is forbidden while a magnetic moment term is allowed. And this is because in a magnetic moment term, the sign between the term and its Hermitian conjugate is inverted. So for a mass term, the contributions to the that enter via the regular fields and the charge conjugate fields would cancel each other, whereas for a magnetic moment, they would add constructively. And therefore, the Voloshin mechanism helps reconcile neutrino magnetic moments with small neutrino masses. They are still at the loop level, because this is only an approximate global symmetry. It'll still be broken at the loop level, but now you have gained at least a loop factor. And this helps quite a lot in making neutrino magnetic moments viable, even for TeV-scale new physics. Without tuning. I mean, with tuning, you can always achieve it. The final slide here, one particular realization of this is a scenario with two leptoquarks. And this is interesting because the two leptoquarks that you can introduce and that can then give you a magnetic moment that could be observable by xenon, these are precisely the leptoquark representations that you need if you want to explain certain anomalies in B physics. I'm talking here especially about the RD star and RK star anomaly. So remember, RD star is would come from a tree-level leptoquark exchange. RK star would be due to leptoquark exchange in loops. So the interesting point is that the quantum numbers of the leptoquark you need in order to generate a magnetic moment for neutrinos are exactly the same quantum numbers as what you need to explain those anomalies. In fact, for the B physics anomalies, even one of those leptoquarks would be enough, the S1 leptoquark. But then in order to avoid tuning, it's possible to introduce a second leptoquark and make them a Voloshin doublet. Okay, this brings me to the end of my talk. To summarize, I've introduced neutrino magnetic moments as a very generic prediction, both in the standard model and beyond. In the standard model, unfortunately, they are too small to be observed. Maybe we'll come up with some ingenious way of looking at them in the future, but for the moment, we don't know how to observe the standard model values of them. But in BSM theories, they can be much, much larger and well within experimental reach. If that's the case, we could see them, for instance, in dark matter detectors, in cosmology, in astrophysics, and in terrestrial experiments using accelerators. And finally, there's this potential connection to B physics anomalies that might be worth exploring if any of the anomalies, either xenon or the B physics anomalies, get more confirmation. Okay, this is all I wanted to say today. So thank you very much for your attention, and I'm happy to take more questions.
Okay, thank you very much. So any questions or comment?
Hi, Joachim. This is Byung-won.
Hi.
Hi. Thank you for nice talk. And so near the end of your talk, you mentioned about this Leptoquark models. So suppose you solve the B physical anomalies by Leptoquark scenario, and then what is the typical size of the magnetic moment in such?
Oh, it's about what XENON1T observes.
Ah, okay.
That's the beauty of it. You end up in the same parameter range. So because as I showed that in order to get magnetic moments of that order of magnitude, you need new physics at roughly the TeV-scale. So that fits quite perfectly with the idea of TeV-scale new physics. If the xenon anomaly was indeed due to magnetic moments, that would fit quite nicely our general picture of where we think new physics might be hiding. So that would be quite exciting.
Could you show the previous slide? Yeah. Yeah, here what is the reason for introducing R2 tilde? I mean, two types of Leptoquark.
The only reason is this Voloshin mechanism. So
okay.
in order to make the smallness of neutrino masses more natural and less tuned. This is the only reason to introduce this second Leptoquark. Because then in the neutrino mass diagram, the contributions from the two Leptoquarks will partially cancel each other. Whereas in the contribution to the magnetic moment, they will add up. If I introduce only one of them, then I would predict neutrino masses that are way too large, and I would have to tune them away.
I see.
Which is a bit not impossible, but maybe a bit ugly.
Any other question?
Actually, I have a similar question. So if you Leptoquark console RD star and RK star, can it also affect a simple leptonic decay like B to mu nu and B to tau nu?
We did look at this. I did not look at myself. My collaborator Admir Grelio looked at this and concluded that this is not a problem. But unfortunately, I don't remember the details off the top of my head. I remember we had this discussion because, yeah, of course, you could think about the relevant diagram. We had this discussion and concluded that it's not a problem, but I don't remember the details, unfortunately.
Okay, thank you.
Thanks.
Question or comment?
Okay.
Okay, if not, then let's thank speaker again. Okay.
Well, thank you very much for the invitation.